Alright, let's move on to the next topic. We are not going to derive the ideal gas equation, but we are going to work on with the ideal gas law. If you wish to see the derivation of the ideal gas law, I'm very happy to do that for you. If you want to email me, I'll personally do that, but there's just no reason to. Here is at the bottom of this screen, though, right down here, this is the ideal gas law right down here. Please do not confuse the ideal gas law with the combined gas law. Notice that you don't have P1 V1 over T1. You have 1P, 1V. We have our N popping back up. Let's remember what that N stands for. In this case, N stands for the number of moles. Number of moles. And then R is a very important number. R is your ideal gas constant. Now, that R has one purpose in life. R is called your gas constant, and the only purpose it serves in life is to cancel units. Now, students sometimes have trouble with this, that its only existence in life is so that units will cancel, but also that it's called a constant, and yet it can be more than one number. And the reason that it can be more than one number here is because of pressure. Let's talk about all the different numbers that we've talked about pressure can be. Pressure can be 1 atm, so we can have pressure in atmospheres. We talked about, that pressure was named for a guy, that Italian dude named Torricelli. So standard pressure is also 760 torr for Torricelli. It is 101.3 kPa. So just these three right here, and there are others here in the United States. We use PSI. It's 13.6 PSI just here in the United States as well. So because we can have all these different units for pressure, and because the only purpose in the world that R right there, the only reason that it's in the equation is because we have to be able to cancel our units to get our answer. If we can have three or more different units for P, we can have three or more different numbers for R. So there's two different ways that you can go about it. You can learn all these different numbers for R. You can look them up each time, or you can learn how to figure it. That's the way I personally chose how to do it, and the way I usually show my students, because then again, you're not bound. You don't have to ever memorize it. You can calculate it each and every time. So here are the units, all the different ones. Notice that they're all, those top three especially, are in liters. Liter atmosphere over mole kelvins. Liter atmosphere over mole kelvins. And then the middle one there, the second one, is liter torr over mole kelvins. Liter bar over mole kelvins. I'm much more partial to liter kPa over mole kelvins. That's 8.31. That's what mostly everyone uses, which is the second from the bottom. A liter kPa is the same thing as a joule. So the second one from the bottom is the one that's most commonly used. A liter kPa over mole Kelvin is 8.31. That's the standard, 8.31 liter kPa over mole Kelvin. So you can either learn all of those or pick one and stick with it, and you always have to make sure that your pressure is in kPa's in that case. Or learn how to derive it yourself. And I personally, as I said, I would like to show you how easy it is to do that. We know that this is at STP, and those units that STP stands for, the S is for standard, the T is for temperature, the P is for pressure. Well, we know pressure in this case can be any of these things. 1 atm, 101.3 kPa's, 760 millimeters of mercury, or 760 torr. all of these different things that it can be. It's going to affect what your value for R is. Well, standard temperature is always 273 Kelvin. So if you set this up and you say, okay, what is my pressure? Well, let's let pressure be ATMs this time. So my pressure, standard pressure, is 1 ATM. Well, I know my 3 mole conversions at 1 atmosphere. How many liters is that? If you remember those mole conversions I told you to know, that's 22.4 liters. For how much? For 1 mole of any gas. Any gas takes up exactly 1 mole. Remember that mole conversion that I told you to learn? Yep, coming back. So let's find our R. And what's our temperature? 273 every time. 273 every time. So let's calculate. Well, 1 times 22.4 is 22.4, and those units are going to be liter ATMs equals 1 mole times 273 times our R. Well, 1 times 273 is 273, so if we're trying to get this R by itself, you're going to divide by 273. And 22.4 divided by 273, I'm just going to bet you money that it's 0.8206. I'm just about to bet you money. And notice what our units are: liters, atmospheres, over moles, and Kelvin. That's what our R is. And that's exactly what they got right there, because we made it so. And indeed, that's exactly what I got. 0.082. I actually got 0.082056. So that's what you're going to have to do. Okay? All right. But that's where they got each and every one of those numbers. So if you learn how to calculate it, you don't have to memorize all those. You're going to always say 22.4 times whatever your standard pressure is, and always divide it by 273. That 22.4 is never going to change. The 273 is never going to change, because those are values at standard temperature and pressure. You just need to decide, well, what is my unit for pressure that I want? Okay? And they're showing you this right here. Okay? All right. And this is saying calculate the volume of 1 mole. A mole is 1 mole of ideal gas at room temperature. That's 25 degrees Celsius. What have you got to do to that degrees Celsius right away? You got to right away say, that's in Celsius. I need to change it into Kelvin. This cannot stay in Celsius. I got to add 273 plus 273 to change it to Kelvin, and 1 ATM. So you can use PV equals nRT, and I'm looking for volume. So how am I going to get that P by itself? V by itself. I'm going to divide by P, divide by P. Okay? So what's my N? My N is 1 mole. My R, in this case, my R is going to be the 0.08206 liter ATMs over mole Kelvin. My temperature is 298.15 Kelvin, and then on the bottom I'm going to have my 1.00 ATM atmospheres. Now please watch what's happening here. This mole is going to take out that mole. This atmosphere is going to take out that atmosphere. This Kelvin is going to take out that Kelvin right up there. And so I'm going to say 1 times 0.08206, and then notice what my units are going to be left with right here, liters, which makes sense since I'm looking for volume. So I'm going to take my trusty calculator. I'm going to say 1 times 0.08206 times 298.15, and I'm going to divide it by 1.00, and I'm going to get 24.5. So my pressure here is 24.5 ATMs. Oh, I'm sorry. I'm not looking for pressure. That is my bad. I'm so sorry. I forgot I was looking for volume. I thought that's really high pressure. I'm looking for volume. So my volume is 24.5 liters. That makes more sense. Volume. Okay? Which is what they got. All right? And then look at what some of the things that we can do. We can use the ideal gas law to find the density of any gas. You can find out the density of a gas. So what would that be used for? Well, so that you know if a certain gas, if it would be feasible to use that gas in an air balloon. Is it going to sink or float in air? You know, you would hate to fill up all these balloons for a birthday party or whatever, and then they sink to the floor, you know, because they won't float in air. So these are many applications, all right? Carbon dioxide is effective in fire extinguishers, partly because its density is greater than air, so it can take away their oxygen. Calculate the density of CO2 at room temperature, and it shows you exactly what to do. Its molar mass is 44.01, okay, and it shows you the density of air at room temperature. And see exactly what it shows you to do. That capital M is the molar mass of air, okay, or it's not the molar mass of air, that's the molar mass of carbon dioxide. So that M, capital M right there, is the molar mass. So you got your pressure, you got your molar mass, and divide it by R and T, and you get your density. Okay? And the density of air is approximately 1.2. So this is more dense than air, so it's going to sink to the bottom. All right? That's pretty handy and pretty straightforward and simple. And you can see some other things. Now, here we have a balanced chemical equation. I sure hope you remember your stoichiometry, because you're going to be able to use it. Notice here, please. All of these stoichiometry truths we can use as ratios to do dimensional analysis. From our balanced equation, you can see that 1 mole of O2 equals 2 moles of CO, carbon monoxide, or you can do the same thing for liters or milliliters. Liters is important here because these are gases, and you can use liters in gases because you can use your 22.4 liters of a gas equals 1 mole. Okay? And the milliliters works the same way. You can use the balanced chemical equation coefficients to compare liters to liters for gases at STP. They must be gases, and they must be at STP, and you can use them. Okay? So, if you have this, if you have, here you have sodium, you can't use it, but you can use sodium chloride. You can use the chlorine gas in this case, all right, to figure out how many liters of chlorine gas that you can have. Here you have some carbon dioxide gas, and you're making some oxygen gas. and it's asking you what volume in liters of carbon dioxide is going to react. So you can work this problem. Okay? Again, your volume of CO2, because you know how many grams you have and how many moles of sodium peroxide you have, you can know how many moles of carbon dioxide you will be able to form using your stoichiometry. And if you know how many moles of carbon dioxide, you can use PV equals nRT to find out how many liters of CO2 you can make. All right? I hope you got that. Again, this is just using the balanced chemical equation coefficients. Look what's going on here. You got that volume, 2.5 times 10 to the 5th liters of air. Okay? And there's your pressure, 0.9970 atmospheres, and there's your temperature. Okay? The result of carbon dioxide, how many moles of CO2? So notice what's happening. Your pressure is changing. Okay? What's going to happen to your volume and to your temperature? So you got your P1 and you got your P2. What is your R going to be? Notice what it shows. If your pressure changes, then notice what happens. Okay. P times V over R times T is going to get you your N. What if you're given grams instead? Okay, please keep in mind that if you're given grams, you're going to change that grams into moles. Then you're going to use your balanced chemical equation coefficients. Your balanced chemical equation coefficients. Do we need to go back to that slide? Let's look at these balanced chemical equation coefficients. What do we care about? In this case, let's pay attention to what we care about. We care about, okay, this is sodium azide or azide, and then please notice carefully, okay, you got 50 grams of that, and we want to know how many liters of nitrogen gas, if there was this, if it decomposed, how many liters of nitrogen gas would be given off, okay? So if you had 50 grams of this, how many liters of nitrogen gas would you give off? All right. So our given is 50 grams of the sodium azide, and our unknown is liters of nitrogen gas. Got that? So we're going to, first thing that we're going to do, our given is 50 grams of sodium azide, and we're going to change that into moles. We're going to use the molar mass to change 50 grams into moles. And once we have our moles, now then we're going to use our balanced chemical equation coefficients. Remember that stoichiometry stuff? Use your balanced chemical equation coefficients to change from moles of sodium azide to moles of nitrogen, because we can't find how many moles, how many liters of this. It's not a gas, it's a solid. We can find how many liters of nitrogen because it's a gas. So we're going to find out how many moles of nitrogen gas are generated, okay? And then once we do that, now we're going to use our PV equals nRT to find out what volume. So get that V by itself. We're going to divide both sides by P to get rid of the P. We know our pressure. We know everything now but the V. So we know how many moles. It's 1.15 moles. We know our R. In this case, our pressure is in atmospheres again. So our R is going to be our favorite 1.08206. And we know our temperature. It says it was 85 degrees. We know we have to add, didn't it say it was 85? Yeah, I believe so. We have to add 273.15 to that. And our pressure was 1 atm. So we're going to say 1.15 times our R constant, 0.08206, times our 85 plus 273.15, and then we're going to divide it by 1 atm, and we get 33.9 liters. Okay? See how that's going to work? It's not that bad. I really do enjoy them. It's not that bad. Okay? And I hope you get that.